data-driven methods to characterize the dynamics of buildings, which I will give together with Christoffer has just introduced. Yes, I have been the work package leader for Work Package 3, and the title of Work Package 3 is Intelligent Energy Systems Integration. And yes, it's about integrating things. So we're looking from two sides, from two perspectives: the demand side perspective, where very much, as you also heard, I'm from DTU Civil Engineering, so we are focusing quite a lot on buildings. Buildings constitute 40% of the energy use in society in Western world, and in many places otherwise in the world as well. So we need to focus on buildings, but we need to focus not on individual buildings because they are so extremely different. On the other side, the supply side, we need to analyze buildings in context with the possibilities to provide energy and to distribute, store energy, etc., on the societal level. So this leads then in all buildings, let's see how are they able to supply energy flexibility. As I already said, it's not enough to look at individual buildings. We need to look at them from an aggregated perspective. And what leads to what we should talk most about in this short presentation is about how can we monitor things that happen in buildings and do smart things with the data that we can collect from that. But first of all, this thing about flexibility, I think we've seen pictures like this frequently before, but very often it's a matter of reducing the peak demands and also having the demands to match as much as possible also the supply situation. So therefore, for instance, this thing about making this peak minimization is one issue that significantly also the buildings can provide to the energy system in society. So from a building perspective, what we can do and what we do much better is that we can use the possibilities for buildings to be well thermally insulated and in this way energy upgraded, but also to use the thermal mass that we have in buildings as a possibility for heat storage and thereby energy storage. Just a few examples how we have analyzed that. We have two generations of old houses, a very old house, which is more than 150 years old. Then if we want to have this flexibility, what happens if the district heating provider, if they cut off the heat provision for a number of hours, what will happen to the thermal comfort of people in these houses here? And for the old house, well, it takes like 2.5 hours before they will begin to freeze. For the other one, significantly newer, but still relatively old from today's perspective, it's only 1.7 hours. The one from the 60s may be better insulated, but has less thermal mass. So that's some of the things we are considering. But we can improve the houses. So even the old one from the 1850s, can have an increased number of hours that the heat can be cut off if it's renovated. So then before it was 2.5 hours, now it's 4 hours. And then of course the new house may not have so much thermal mass, well, depends, but first of all, it's much better insulated, and then they can sustain, the occupants can sustain for 8 hours without heating. So that's something that's worthwhile analyzing. I said already, I think a couple of times already, that buildings and users are so individual. So here's a study where we looked to 16 houses in this town of Sønderborg in Denmark. And you can see, of course, how different patterns there are over these 24 hours of a day of heating power use, as we see. So we need to see these things, the individual houses in combination. We need to focus on aggregation. And then we get the pale rose curve on the top that we should be focusing upon, but we can see in the bottom how each of the individual buildings contribute. So that's something we must consider. By the way, the light blue curve, that's for the solar gain. So that's also something that's worthwhile considering. So how is the situation with the outdoor environment? Now, there's kind of individual possibilities of different patterns. If we can shift them somehow, you can use the physical thermal storage in buildings, but just by shifting, it's also something that we can control when we look to the aggregated pattern. So this kind of virtual storage by intelligently shifting the profiles, that could be useful. And also if we can kind of model the future some hours ahead, that would also be beneficial. So model predictive control is also an issue we've been looking to in work package 3. So, but all this leads to that we cannot use it without knowing better the characteristics and the performance of our buildings. And that's the last point I will mention before I lead the word over to Christoffer, is the necessity to measure. So all in these houses, we're gonna measure and monitor what's going on. And that goes along with recent also incentives from the European Commission. Many of you may know the Energy Efficiency Directive. I just read aloud a few words, that by way of example, in a district heating network where metering data are transmitted and collected automatically on an hourly or daily basis, such data will represent a significantly higher value compared to if we had a monthly data, that's as it says in the bottom of this text here. Also in the Energy Performance of the Directive, which is the amendment that came 2 years ago, it also talks for that we should have digital solutions in the built environment, which will give us better opportunities for energy savings, first of all, but also by providing consumers with more accurate information about their consumption patterns, then we'll also enable system operators to manage the grid more effectively. Yet another piece of text that I just think is interesting, also in the EPBD directive, is that we should have electronic monitoring, they say, and that would provide the potential to provide cost-effective and significant energy savings. And the last piece of text I have got from the EPBD directive is about their incentive for non-residential buildings, that they should be they should have building automation and control systems that are capable of continuously monitoring, logging, analyzing, and allowing control of the energy use. There's also, this is what's for non-residential buildings, and there's a similar clause for the residential buildings, which will come afterwards. Now, all this, that leads to the need for measuring, for logging, for monitoring our buildings. And we can do it with heat meters. We can have indoor climate sensors. We can have motion sensors that either detect if we are present, but also detect the motion of our windows and doors, etc., if that matters. And also we can have clamps that can register our electricity use as well. So it can be extremely extensive what we need to measure. And even here the list is longer also with outdoor climate, of course, we need that. We can make thermography of our buildings, etc., know about the air tightness. We can measure so many things, and we are on a path where we are doing this more and more. But gee, this can be extensive, and do we really want to live in such buildings, etc.? It's expensive for the buildings owners, and maybe troublesome, bothersome for us who live in buildings and use the buildings. So we have in the project, we have developed a concept whereby we can use mathematics and statistical methods so that we can do with not having so many sensors, but we can use few sensors and collect data from them in an intelligent way, as long as we collect data with a high frequency. So with that was kind of introduction to really how we then do it. And that is over to Christoffer to show his work. So thank you for me for now.
Thank you, Carsten. I'll see. Okay, yeah, so in continuation of Carsten's words here, I'll show you a few examples of how we actually can go and estimate some thermal performance parameters of buildings. One example is a gray box model based on stochastic differential equations. This picture here, it shows a schematic overview of a deterministic system where we have some heat input, some outdoor temperature and solar gain. And from that we can estimate a number of parameters and actually functions, which is embedded in these formulas here. If we look in here, we can see these highlighted variables. It's actually parameters. The R's here, that's the thermal resistance of the buildings, which are at least to some extent unknown. And we have some heat capacities, which of course is very related to the flexibility of the building. These parameters, we don't know them exactly, but from data we can actually estimate them. And we can estimate both like constants, but also functions. Now in one of Carsten's slides, he mentioned the solar gain in the building as a rather important factor, which we actually have worked on. But some of the parameters here, that's the heat loss coefficients. We can calculate from the thermal resistance of the building. We can get the heat capacities directly from the model, and we get time constants. And beside that, as I mentioned, we can also estimate some functions which are actually unknown to us in the beginning. So in this case here, we would like to try, this is just an example showing, getting an idea of how it works. It's not exactly how it works in the gray box model, but let's take a look. So here we would like to estimate how much solar gain do we get into the building during the day. So, or in other words, depending on where the solar is positioned, the sun is positioned. So here we have we estimate a constant for all the diffuse solar gain getting into the building, and the red line here, that's the solar gain from the direct radiation, which is estimated by a spline. And you can actually see it here in this animation, how we can optimize these functions to actually estimate how much solar gain we have in the building, like this. We have published a paper about this in this one. And another method, which is, it's rather different. I mean, we still estimate the parameters related to the thermal performance of the building, but in a very simple way in terms of how much data you actually need and so on. So in this case, we have tried to go in and say, okay, what if we only have the heat consumption for the building and the weather data? What can we actually do? And the reason for that is, first of all, that we would like to reduce the number of sensors in the houses because it's expensive. They can fail and so on. And the other thing is that the indoor temperature, for instance, which is often very critical to obtain to do these models, it's actually not that easy to measure. I mean, it's not difficult to measure, but it's difficult to measure the representative indoor temperature. So in first example up here, we have measured this is an unoccupied test house, but we have measured the temperature in different heights in the same room. And we observe a temperature difference of up to 5 degrees. In another example, which is an actual real apartment from Denmark, we have measured in different rooms. And we see from room to room, we can actually have a temperature difference of up to 10 degrees, which is, I mean, this is really extreme, and that will really affect the estimates from the model if we don't know like a good representation of the indoor temperature. So in this model here, we will try to neglect the measurements of the indoor temperature and actually still calculate the thermal performance. And we do that by taking an old method called energy signature and combine it with a smooth maximum function to get a continuous function where we also get an idea about the transition period and so on, and the standby effect in the summer. And from that, we came up with this model where we estimate the heat consumption, the daily heat consumption, I should say. And we take this smooth maximum function, it's called a log sum EPS function. So we take this function, feed in some input to it, and it can be, in this case, the weather dependent heat consumption. So in this case, it's dependent on winds, outdoor temperature, and solar radiation, and a constant weather independent heat consumption, which is the heat consumption during summer. So that could be related to system efficiency or hot water and stuff like that. And then in the end, we have some noise in the data and the model. From that model, we can actually predict the heating power day by day. So all the white dots, they are showing the measured heating power, and the black dots might be a little difficult to see it, but the black dots, that's the predictions. And this black line, that's a smooth results of the prediction. So from that, we can actually go in and say something about how well is it insulated, what is the U value. In this case, we have the floor area, so we can come up with a U value and a UA value. We can say something about the sensitivity of wind. So if it's blowing a lot, is it then losing a lot of heat? That might indicate that we have some issues with the air leakages and so on. Yep, and then we have a GA value, so how much solar energy do we get into the house, standby effect, and then some numbers describing the transition period. And finally, we have actually estimated some effects of the occupants. This is described further in this article, and I think that will be it for me and Carsten.